Welcome everyone to the Eberle Design webinar on flashing yellow arrow for 33X cabinet. This webinar is going to go through some of the basic configuration for a 2010 ECL, 2018 ECL, or 2018 KCl type monitor used in a Caltrans 332 style cabinet, and we're going to demonstrate how to configure it for flashing yellow arrow operations. So several weeks ago we had a webinar that we provided for similar functionality in a TS2 cabinet using an MMU2 16LE. What we'll find in this seminar, it's a lot of similarities, but the equipment is very different and the modes are subtly different. So if you're looking for information on an MMU, I would encourage you to go back to our website. You can replay that webinar. This particular event is for 332 style cabinet users, basically the 2010 ECL. So let's start off with a little bit of background on flashing yellow arrow. Flashing yellow arrow, while it may be new to your agency or new to you, it's been around for about a decade now. Federal Highways started giving approvals for testing back in 2006. So one of the benefits of flashing yellow arrow is that it provides a very clear way to implement the protected permissive left turns without the yellow trap and with complete control over what the motorist, the left turn motorist, actually sees. So at the time, Federal Highway did a study across North America, and they found somewhere above 10 to 12 different ways that agencies were implementing protected permitted left turns. That's pretty confusing for motorists as they travel around the country. So one of the motivations was to try and eliminate some of the more obscure ways to do protected permitted left turns and kind of focus on this flashing yellow arrow scheme. So it's been found that it has good driver understanding once motorists experience it a couple times and learn what they're supposed to do. It's an extremely valuable tool for the traffic engineer because it gives them great control over the left turn action, and we can do lead lag, lad league, time of day, queue length, all kinds of different factors can go into determining how to provide the left turn phasing. No louvers are needed. It's not like Dallas did many years ago. So there's a number of advantages. If you're interested in all the details of flashing yellow arrow, there's an NCHRP report from 2003. It's NCHRP 3-54, and it goes through the background of flashing yellow, many of the different aspects, and it's basically the study that was provided to MUTCD to develop the rules and guidelines for deploying flashing yellow arrow. So EDI first got involved early back in 2005 to provide a monitor for these test intersections to do flashing yellow arrow. In 2009, the MUTCD released their formal signal operation definition of flashing yellow arrow, what the signal faces look like, how they're oriented, how they should operate, that type of information. And not too long after that, NEMA, the NEMA Transportation section took up an action item to develop the flashing yellow arrow amendment for the NEMA TS-2 standard. So between those two documents, it pretty much defines how we implement and deploy and design flashing yellow arrow, and for the equipment, how it is intended to operate. So we have an equipment standard, we have an MUTCD standard. Now, I mentioned that this is a great tool for the traffic engineer. For the signal cabinet maintenance technician, it's pretty much of a headbanger. Basically, the premise is we have a 4-section signal head now, and yet all of our equipment is designed around 3 sections, red, yellow, and green. The flashing yellow arrow has a red arrow, solid yellow arrow, flashing yellow arrow, and solid green arrow. So one of the problems here is trying to get 4 signals monitored with equipment that is intended to drive 3 signals. So we'll get into how we do that. We're going to pair up 2 channels, but basically in these 3 products, the conflict monitors for 33X or 332 style cabinet, we provide 2 basic modes for configuring flashing yellow arrow. So the first mode, we just call it the FYA standard mode. It's fairly straightforward, but it does require an aux file to be installed in the cabinet. So that gives us our full 16 channels of operation that the 2010 ECL monitor supports. We're going to be using 2 load switches and 2 monitor channels per approach to get the flashing yellow arrow 4-section signal monitored. The second mode, which is a little more obscure, is called the FYA C mode, the FYA compact mode. The compact mode is, as you're going to see later in the presentation, requires remapping of the controller. It requires some special cabinet wiring, and it requires some remapping in the monitor. So all of this can be made to work, and if it's documented clearly, it can be easily deployed, but it does add another level of complexity to setting up and deploying flashing yellow arrow. The reason for the compact mode is it only requires a standard 12-position output assembly. So if your cabinet doesn't have room for a aux file, or you don't have the budget for an aux file, or for some reason you don't want to use an aux file, we can do 8 phases, 4 flashing yellow arrows, and 4 PEDs using the 12 load switches found in a standard output assembly. So we'll see how that works couple slides down. So the paired channel concept is how we combine 2 load switches and 2 channels to get our 4 active signals. So as the picture shows there, what we're calling load switch B, which is usually called the overlap channel, that has the red arrow, the yellow arrow, and the flashing yellow arrow. That's our permissive turn channel. And load switch A in this example is the protected green arrow, so we're only going to use 1 output of that load switch. So by combining these 2 channels into a pair, the monitor knows that all 4 are related. All right, now we have to do something with the unused red and yellow output of load switch A, the protected load switch, because due to load switch leakage current, if a load switch output is unloaded, no signal heads attached, the monitor will sense it as an active signal. So there's a number of choices there. The 2010 ECL monitor has some yellow disable jumpers on the program card. So if we install a yellow disable jumper there, that will blank out the yellow. If you want, you could put dummy load resistors in the cabinet on the red and the yellow and get a similar effect. But we have to do something with those 2 unloaded signals. We'll have a little more about that towards the end of the presentation. So let's see what an FYA mode looks like. On this slide, the image that we're seeing there of the 16 channels is basically how the monitor views the assignment of the phase to channels. So in this case, our channels 1, 3, 5, and 7 are the protected turn channels. Channels 9 through 12 are the permissive overlap channels. and 13 through 16 by convention are our pedestrian channels. Okay, so the beauty of this setup is everything is straightforward. Again, it requires an aux file because channels 9 through 12 come into the monitor from the wiring to the aux file. But no controller I/O mapping is required, no monitor remapping. There's no other wiring in the cabinet required other than that to hook up the aux file. So the first 4 load switches in that aux file correspond to 9 through 12, channels 9 through 12. So there's another little intersection diagram there of our typical phase assignments for a 8-phase type quad intersection. So additionally, in this case, what we want to do to program the monitor is, again, all of the conflict matrix, the diode program card is going to be cut according to the assignments shown in the picture. 1 and 9 are paired together, 3 and 10 are paired together, 5 and 11 are paired together, and 7 and 12 are paired together. So that channel pairing is fixed in the monitor. So I've got some slides here showing how we would program this on the actual monitor itself. One for the 2010 or 2018 ECL, it's a dip switch programmed monitor, and a separate slide we'll get to after this one on the 2018 KCl monitor. So a couple of things. Number one, we have to tell the monitor 2 things about the flashing yellow arrow mode. So there is a dip switch labeled FYAC. We want that switch to be in the off position. So on EDI products, the name that we provide for the dip switch is the functionality that you get when the switch is in the on position. So since this switch is labeled FYAC for the compact mode, we want it to be in the off position for the standard FYA mode. There are 4 additional switches labeled with the channel pairs, 1 and 9, 3, 10, 5 and 11, 7 and 12. For each of those switches, we're going to turn that switch on to enable a flashing yellow arrow pairing. So if an intersection has all 4 approaches are flashing yellow, clearly we turn on all 4 dip switches. If perhaps only Main Street has flashing yellow arrow, you would find switch 1 and 9 and 5 and 11 turned on. So we're going to just enable those 2 pairs. When we do that, the other channels, 3 and 10 and 7 and 12, because they're not enabled, they are still can be used as normal channels. They could be protected turns, through phases, overlaps, whatever you want to normally assign to them. So now we have to configure the monitor for the monitoring functionality for dual indication and clearance. We use the SSM switches for this purpose, and the programming for the flashing yellow arrow channel pair is done using the SSM switch for the overlap channels, in this case 9, 10, 11, and 12. So because we want to monitor this flashing yellow arrow movement for all possible monitoring faults, dual indication, short yellow, skipped yellow, we want to turn the SSM switch on for those channels. Now the protected turn channels, 1, 3, 5, and 7, are a little different. Normally, the SSM switch is left in the off position for the protected turn channels, 1, 3, 5, and 7. So the case where we want to do some programming for those channels is if we have signal lamps connected to the red and yellow of the protected turn channel, then we want to monitor that channel appropriately. We might want to do this if we have a hardwired right turn overlap. In other words, that right turn overlap signal is connected to the associated protected left turn. In that case, we're going to have signal loads on, let's say, channel 1, red and yellow. If that's the case, then we want to turn the SSM switch on for that protected turn channel. So the subtle difference here is that the SSM switch for channels 9, 10, 11, and 12 control the monitoring function for the flashing yellow arrow 4-section signal, and the SSM switches for channels 1, 3, 5, and 7 only affect channels 1, 3, 5, and 7. So in that case, the green arrow is kind of shared between both the channel pair and the channel itself. All right, and there's a table below that shows how to program the conflict matrix, which channels are permissive with which channels. This assumes a standard 8-phase quad and doesn't include the PED. All right, so the next slide shows the same type of programming if we're using the 2018 KCl model. The difference being that the ECL models, whether it's 2010 ECL or 2018 ECL, one is a 16, one is an 18 channel monitor. For the 2018 KCl, all of the programming is done with a data key. So there are no dip switches, there are no diodes to cut. We program in the data key, actual configuration data, and away we go. So in this case, the monitor functions still need to be programmed in a similar fashion. We're going to click on a mouse to program the data key using our monitor key software. And there's a little more detail involved in the programming because it is data. We're not limited by dip switches. So I won't go through all the settings, but if you're programming up the 2018 KCl, this is kind of an example template for setting up that unit. So that's the flashing yellow arrow standard mode. Again, everything is 1-to-1. The controller drives channel 9 for the overlaps. When we want to do a flashing yellow arrow sequence, it would go from channel 9 red to channel 9, the green would be flashing, indicating the permissive left turn. We would clear it to the solid yellow of 9 and then return back to channel 9 red. In the case of the protected turn sequence, we go from channel 9 red to channel 1 green. Then to clear channel 1, we would go back to channel 9 solid yellow and then to channel 9 red. So pretty straightforward. Again, no clever I/O mapping, but it does require the installation of an aux file. So now let's look at the flashing yellow arrow compact mode. All right. The idea here is we don't want to use an aux file for some reason, so we're going to remap some outputs to collect our channel pairs. Now there's a couple of restrictions here. Number one, as we'll see in a minute, this requires some special wiring to be in your cabinet. This wiring is required by Caltrans, so if your cabinet is truly Caltrans approved, it will have that wiring. But outside of California, I know there are cabinet manufacturers and agencies that don't put that wiring in, and so it's something you need to look into before you try and deploy the compact mode. So in this case, what we're going to do is we're going to reutilize the PED yellow outputs to drive the protected green arrow signal. So instead of requiring 4 additional load switches, which we have no room to plug in, we're going to use the 12 that we have and retask those PED yellow outputs to be our protected greens. So to do that, we have to assign them to remap them in the monitor to channels 9 through 12. That means we need our permissive overlap phases to be now assigned to 1, 3, 5, and 7, the odd phases. So you'll notice the subtle difference between the standard mode and the compact mode. We've swapped the position of the protected and the permissive left turn channels. All right, plus we've remapped the PED yellows. So the picture there kind of shows what you see on the front of the monitor when this is cycling, with the exception of the PED yellows. So when the controller wants to drive phase 1 protected left turn, the controller is going to turn on the phase 2 PED load switch, which is load switch number 3, turn on the yellow. That's going to get remapped through cabinet wiring and the monitor to appear as channel 9 green. Okay, so it's a little trickier to watch the cabinet cycle, but after a little practice, you get pretty used to it. Again, if your controller doesn't have the capability to do I/O mapping, this won't work. If your cabinet doesn't have the Caltrans PED yellow wiring I'm going to show you, it won't work. So before you get moving down this path, make sure you have all the resources you're going to need. So the first thing we need to discuss is the compact mode cabinet wiring. So Caltrans, when they developed the 332 cabinet many decades ago, they felt that monitoring the PED yellows for a conflict condition during PED clearance was not something they wanted to do, so that left them the option of reusing the yellow output of the 4 PED load switches for some other purpose. What they had in mind was to collect those 4 PED yellows and reroute them to the monitor to appear as 2 right turn overlaps, 2 section overlaps with just green and yellow arrows. So when we look at the compact mode mapping, it's kind of 2 stages. The top graph there, or the top table, is showing us the cabinet wiring. So from load switch number 3, the yellow PED yellow output is actually wired up to monitor channel 9 green input. Likewise, PED 4 yellow, load switch number 6, is wired as channel 9 yellow. So if you were going to do a 2-section right turn overlap, you remap your controller to drive those 2 PED yellows, and the monitor will see them as channel 9 green and yellow. Likewise, for the next 2, they're configured from load switch 9 and load switch 12 into the monitor as channel 10 green and channel 10 yellow. So again, by remapping those 4 unused PED yellows, we kind of get 2 2-section green and yellow arrow signal heads monitored for free. All right? So that gets the PED yellows into the monitor. Now we've got to spread them out because we're not using them as a 2-section signal. We're looking for 4 separate green inputs. So what the monitor does when we tell it it's in the compact mode is it will now remap those 4 signals again, whereas channel 9 green stays as channel 9 green on the monitor. Channel 9 yellow gets processed as channel 10 green. Channel 10 green gets processed as channel 11 green, and channel 10 yellow gets processed as channel 12 green. So again, there's remapping going on in the cabinet wiring and remapping going on inside the monitor in the software. So the end result is the picture that we saw in the previous slide, where we have our protected green arrows on channels 9 through 12 and our flashing yellow arrow overlaps on 1, 3, 5, and 7. And the pairing combination is identical to what we had in the standard mode. 1 and 9 go together, 3 and 10, 5 and 11, and 7 and 12. Okay. So again, make sure your cabinet is wired appropriately. What you'll typically find in the output assembly when you pull the back panel down is some white Molex connectors. There's likely going to be 3 of them. This may be cabinet manufacturer dependent, but one of them goes to the monitor, one of them comes from the PED yellow load switches, and the third one would come up from the aux file. So you have to plug in the Molex connectors appropriately if you're going to use the aux file in the standard mode, or in this case you're going to use the PED yellows for the compact mode. I'll point out one other thing, and this bothers a lot of seasoned technicians. In this case, because of the phase to channel assignments, channel 1 and channel 2 are permissive. Channel 1 being the flashing yellow arrow, channel 2 being the opposing through phase. So the first diode you're going to cut, which you've never cut likely in your whole career, is the diode labeled 1 and 2. So we just need to get over it. We've rearranged the convention here to suit our flashing yellow arrow assignments. So again, the permissive programming is going to be different than you've done before, but using these phase to channel assignments, that's the way we need it to be. So again, a simple example here perhaps of as we cycle. So I've picked phase 7 left turn as an example. So what we'll see as we're looking at the cabinet when we want to serve phase 7 protected left turn, the controller unit is going to drive load switch number 12, which is our phase 8 load switch. It's going to drive the yellow, and you'll see the yellow indicator on the front of the load switch come on. The monitor, however, because of the remapping through the wiring and the remapping internal to the monitor, will display, in this case, channel 12 green active. So again, all of the programming for the monitor relies on this final mapping result. So channel 12 is the signal that we want to use for programming the program card, the diode card, and programming the switches. All right, so the next slide shows an example of programming again, the 2010 or 2018 ECL monitor, the dip switch style. In this case, we want the option dip switch labeled FYAC to be in the on position. That selects the compact mode. And likewise, for each channel pair that has a flashing yellow arrow approach, we are going to turn on the appropriate FYA dip switch, 1-9, 3-10, 5-11, or 7-12. Now there's a subtle difference here between the standard mode and compact mode. In the compact mode, if we're only using two FYA approaches, as in the previous example, 1 and 9, 5 and 11, in this case, 3 and 10 and 7 and 12 are just disabled. So you can't use them for any other purpose because there is no load switch driving those channels. All right, so we've got it in the compact mode. We select and enable the channel pairs. The rest of the programming is pretty similar. We're going to turn the SSM switch on for the permissive overlap turn channels. So now our SSM switches are on for channels 1, 3, 5, and 7. And again, for the protected turn channels, 9, 10, 11, and 12, we want the SSM switches off. So in this case, again, because we've created those the protected channels, we don't have the option of the hardwired overlaps or any of the confusion there with dummy loads. So I've shown, again, the diode programming for the conflict matrix, and you can see in that first row, 1 and 2 are permissive, 1 and 5, 1 and 6, 1 and 11. Again, add in the PEDs if you've got them, and you've got the programming cards set up. The next slide shows kind of the same basic programming for the 2018 KCl. Again, this programming is all going to end up in the data key, a lot easier than flipping dip switches and clipping diodes, but conceptually it's the same style of programming. So that's an overview of the two different modes provided in the 2010 ECL, 2018 ECL, and 2018 KCL monitors. There's some general things that we should cover as well. Some additional monitoring functions beyond what we normally detect with those monitors. So let's go through those. The first one that may come as a surprise is dynamic clearance conflict detection. Right? So in this case, what this has to do with is whether the solid yellow arrow, when we clear either the protected or the permissive turn, is it going to be conflicting or permissive with the opposing through phase. So when we're driving the flashing yellow arrow, when we clear it, we go to the solid yellow arrow. That solid yellow arrow is permissive with the opposing through phase. So that's where we had to clip the diode 1 and 2, for example. However, when we're cycling through the protected turn, channel 9 green is on. When we clear channel 9 green, we're going to go back to channel 1 solid yellow. In this case, however, the solid yellow arrow is intended to be conflicting with the opposing through phase. So the firmware in the monitor takes care of this, but essentially what it's doing is taking the diode out when it's a permissive left turn and putting the diode back in when it's a protected left turn. So normally you won't see the effect of this, but you do have to remember that if you trip this monitor function and you get a fault, a conflict fault because of the, let's say the solid yellow arrow is stuck on and we go to the next through phase, you're going to get a conflict that kind of goes against what the diode card says it should be. So 1 and 2 are normally permissive. In this case, 1 and 2 are going to be a conflict. So as long as we understand where in the sequence we are when the conflict happened, we shouldn't be surprised. All right, so red fail for a flashing yellow arrow signal is just like our normal red fail, but it includes all 4 signals. So if we have no active signal on the red arrow, the yellow arrow, the flashing yellow arrow, and the green arrow, meaning the left turn signal for that movement is totally dark, that's a red fail. Same with dual indication. It involves all of the possible combinations of red plus yellow, red plus green, red plus flashing yellow arrow, yellow plus flashing yellow, all of the different combinations. We expect one and only one signal to be active across the 4-section signal head at any time. If more than one is on, you're going to respond, the monitor will respond with a dual indication. Clearance is a little bit different. We've already kind of seen the effect of that. When we clear the flashing yellow arrow, we go to the solid yellow arrow and then to the solid red arrow. The protected clearance is a little different though. When we have the green arrow on channel 1 and we go to clear it, on channel 9, we're going to jump directly to the solid yellow on channel 1 and then to the red on channel 1. So again, we involve both channel pairs in the protected sequence. We also will detect when the flashing yellow arrow is stuck on. If it's stuck off, it'll be detected as a red fail. If it's stuck on, the monitor will detect that as a separate monitoring function. That's built into the firmware. If there is a reason that you do not want the intersection to go to flash, if the flashing yellow arrow malfunctions and sticks on, that can be disabled by soldering in what we call Select 15 jumper. It's a soldered jumper on the main PC board. So reasons that you might not want to detect that is, again, if you feel that that's not a fault that's significant enough to put the intersection into flash, it may be a main arterial at rush hour or something like that, you can disable the function. There are also some controllers that don't have the capability to map the signals according to the way the compact mode expects them. We can, in that case, they drive the flashing yellow arrow signals as the odd signal on 9, 10, 11, and 12. So if you are running that controller in that mode, you'll have to turn this function off because the monitor is expecting the flashing yellow arrow to be on 1, 3, 5, and 7, and instead it's going to find it on 9, 10, 11, and 12. So normally we don't have to mess with the jumper, but it's there in case we do. So that's pretty much concludes the overview of using the 2010 ECL, 2018 ECL, or 2018 KCl monitors in a Caltrans 33X style cabinet. Again, it's fairly straightforward because we're dealing with simple monitors. It's not as complex as the NEMA TS-2 MMU. On the other hand, we don't have the flexibility that we have in that other product to service different applications and different mappings. So this presentation, these slides, and this webinar will be posted on the EDI website. If you need to review it again or you want to download the slides in hard copy to take a look at them, I would encourage you to go to our website, www.editraffic.com, and you'll find all this material in the support section. This webinar also qualifies for IMSA TARP points. In the sign-up sheet for this webinar, there was a place to put your IMSA member number and your name and your agency. So if you've supplied that information when you registered, we will take care of submitting your name to IMSA and you'll receive TARP points for attending this webinar. If you failed to provide that information and would like to, you can certainly send us an email to support@editraffic.com and just mention in there this webinar and provide your IMSA member number and we'll add it to the list. So I want to thank you very much for paying attention. Flashing yellow arrow is one of those innovations in our business that I think comes with great benefit, but it's some hoops we have to jump through to make it work in the hardware, and I think your agency, however, will find it worth the time and trouble to deploy. So if you have any more particular questions, feel free to submit them during this webinar. We'll go to a question and answer period afterwards, or if something comes up later, again, feel free to send an email to support@editraffic.com and we'll get you an answer to your question as soon as possible. So thank you very much and have a great rest of your day.